Welcome to my video lab report on the pendulum motion simulation. In this lab, I explored the physics of a pendulum using computational models, focusing on how gravity, tension, and angular forces work together to create periodic motion. By simulating a pendulum with VPython, we aim to model its angle and angular velocity over time. The purpose of this lab is to understand the behavior of a pendulum, specifically focusing on how angle and angular velocity changes over time. Pendulums are classic examples of simple harmonic motion and are governed by fundamental physics principles such as gravity and tension. We approach this simulation using key physics concepts. The pendulum's motion is primarily governed by Newton's second law, where the force of gravity acts to pull the pendulum downwards, while the tension of the rope counters this motion. This creates a net force that changes with the pendulum's position. In small angle approximations, where the angle is less than about 15 degrees, the motion can be approximated by simple harmonic motion. We use the small initial angle in our setup to maintain a nearly harmonic system. Our main result shows that as time progresses, the pendulum's angle oscillates back and forth, while the angular velocity oscillates as well, reaching maximum values as it swings through its lowest point. The pendulum system consists of the mass at the end of the rope, while the surroundings are the gravitational field and air resistance. However, in this idealized model, we ignore air resistance for simplicity. To simplify our model, we set the pendulum length to 39.6 meters with an initial small angle of 0.1 radians. We assume a gravitational force of 9.8 meters per second squared. With these initial conditions and assumptions, we can predict a smooth oscillatory pattern in the pendulum's angle and angular velocity. Now let's take a look at the code. Using VPython, we set up the pendulum's physical properties and use the loop to update its angle and angular velocity over time. We plotted the angle and angular velocity using G-curve in VPython to visualize how they change. Here we can see the output of our simulation, showing the pendulum's angle and angular velocity over time. The simulation aligns with the theoretical expectations for a small angle pendulum. We observe periodic oscillations with the angle decreasing slightly over time due to rounding in the simulation. In our simulation, the main source of error is the numerical approximation. Although our small angle approximation helps simplify the math, this can lead to minor inaccuracies over extended time. Another source of error is rounded within VPython, which might cause minor deviations from the perfect periodic motion. To answer the additional question, what if we increase the angle? At larger angles, the pendulum would no longer follow simple harmonic motion, and our small angle assumption would become invalid. The pendulum would take longer to complete each oscillation and would exhibit more complex behavior. In conclusion, this lab allowed us to model the motion of a pendulum computationally, observing how its angle and angular velocity change over time. By using VPython, we demonstrated the periodic nature of a pendulum and observed minor errors due to numerical rounding. This approach helps us apply fundamental physics concepts to our dynamic model, making abstract concepts more tangible. Finally, I would like to acknowledge the resources and tools used in this experiment, including GlowScript software and the lab instructions provided by my course. Thank you for watching.